thank our speaker again. We'll move on. Thank you, Niels.
Okay, thank you. Thank you for the invitation. So today I'm going to talk about the NanoMagSat mission. So just a quick introduction to this mission. It's an ESA Scout mission, and I think it's important to stress a few things about this. Number one, it's not run like an Earth Explorer, like Swarm. ESA requests a consortium to be built, and this consortium is next in charge of building the satellite, running the satellite, and distributing the data. So this is run entirely by the consortium, but of course with strict ESA checks. And the data will be freely available, as is generally the rule of ESA. The other thing is that this is a constellation with which we are building with 35 million euros, so it's a much lower cost than Swarm. So there are a number of challenges in this respect. So the consortium that we put together is basically illustrated here with the logos, and these are the people who will actually build, run the mission. But we also have, is that working? Yes. Science advisory group. So a number of you perhaps are on the list. And this is extremely useful because that helps us providing guidance, especially that we keep on having back and forth discussions about what is possible, not possible, and what are the requirements, so that we need to have this support from the science community to avoid our industrial partners or ESA to be tempted to relax some of our requirements in a way that would not be too good. So thanks a lot, by the way, to the SAG for assisting us in all that matter. So the mission itself is obviously connected to Swarm, MSS, CSS, etc. And we are obviously looking into the Earth's magnetic fields. There are a number of differences that I want to highlight. These here are the usual targets that we've been discussing already. And so that the point here is the targets are similar to those we've seen. What is different is that we want to capitalize on the low inclined orbits, just as has been discussed. Both Niels and Anya showed that 41 degrees covers the local time very fast. And as Niels pointed out, if you have only one inclined satellite, you either have the, half southern hemisphere or the northern or the southern hemisphere. And if you have two satellites, that you can manage to cover everything, and I'll show this in a second. So the point here is the progress we want to make is by the constellation design. The payload, the rest in terms of measurements is very similar to what we have on Swarm. And that's where we want to expect to be able to contribute to make progress, especially on fast core signals and things like that, because we cover the local times faster. Now, the other aspect of the mission is that we also want to look into the ionospheric environment, and this is a bit different from, actually all missions are a bit different in this respect, because MSS is also a bit different in this respect with respect to Swarm or CSS. And in our case, the idea is we want to have some instruments to look into small scales in the ionosphere, and this is done by having high-frequency magnetic field measurements and also high-frequency measurements of the electron density, and plus a number of tools that we can use, such as the fact that we can have access to waves that propagate within the ionosphere, and these waves are affected by the ionosphere, so they provide some extra information. This is something that we can only partially do with Swarm for the time being. That can be done with CSS to some extent, so each mission has a bit of its peculiarity. And here, the point is that we innovate a little bit in terms of instrumentation. So compared to Swarm, we have a slightly different orbit configuration to improve the local time coverage, and we have different instruments to also look into high-frequency stuff and more details in the ionosphere. So the design hasn't changed since the very beginning. The idea is that we have this polar orbit, which we want to be similar to Swarm, because of course, in terms of inclination, we hope, by the way, we don't have propulsion. We have gravitationally stabilized satellites. And so we want the polar orbit to be, useful in combination with Swarm, especially Swarm Bravo, and Alpha and Charlie, if they're still around, of course. And the two inclined orbits, the important point is that we want to phase them 90 degrees in terms of right ascension, ascending node. That basically means that you shift it by to cover the local times nicely, as I'm going to show later on. The instruments is basically, I'll come back to these in more detail, but we have an absolute magnetometer that will actually provide the vector magnetometer, the vector field. So it's a self-calibrated instrument with star trackers at the tip of the boom, and that will provide the 1 Hertz vector data, very similar to what we have with Swarm. And then it will also provide 2 kilohertz scalar data, which will be complemented by a vector magnetometer, which is a mid boom, also 2 kilohertz. And on Swarm, we only have 50 hertz vector magnetometry. So the idea is to have access to higher frequency. And then the multi-needle Langley probe is, and the idea is that I'll show this later on, is that we can access high frequency as well, 2 kilohertz, while still getting 1 hertz, especially for the electron temperature. And then something that we have also are dual GNSS receivers with 3 antennas, and this will allow us to do some radio occultation. And it turns out that the 60-degree inclination is very nice for that type of investigations. I'll show in a second. Okay, so these are the requirements. I'm not going to go through these, but that has been worked out with the science advisory group and tried to make the best, of course, of the instruments, the payload, and that drove the design of the satellite. And this is a big challenge, as you always know. We don't want the satellite to produce perturbations, so the entire satellite has been designed to avoid this. The orbits, I'm going to show this. Been showing this quite a number of times. Contrary to what Niels was showing here, I'm splitting the maps in terms of local time covered. So that's 1 day. And if you have a map, for instance, the one on the top left, is local time between 0 and 3 in the morning. And so you start filling as the day passes. And after 10 days, you cover this. So blue is the polar orbit, green and red are the inclined orbits. And as you can see, they nicely cover the portion that the other inclined orbit is not covering, so that after essentially 30 days, you've been covering the entire latitudes between -60 and 60. And that's the whole point that we would next use this for typically. So that's 40 days. And that's very useful for trying to recover fast signals. So that's an early simulation that had been done, just illustrating the fact that if we start putting fast signals in the core and try to recover them with this constellation. So on the top left is what you expect. The initial signal, that's the extra signal on top of a chaos model and all of the sources. We try to see if we can manage to recover it. On the right-hand side is what we recover, and the residuals is below. And this is a simulation over 3 years. So obviously, at the beginning of the mission, we're not very good. But if I'm good at starting this, can I start this? Yes. You will see that it does not want to run. Or does it? How do I do it? Oh, there you go. Okay, so we recover nicely now once we're in the middle of the mission. As you can see, the 2 top maps and the residuals are small, and then it becomes not as good later on. Then the nominal lifetime of the mission with respect to ESA is 3 years, but I recall, just remind you that Swarm had a nominal lifetime of 4 years. So hopefully we won't be able to last 10 years, but we expect to last at least 5 years. Now it wants to run. Okay. This is an illustration about the advantage of the inclined orbit for radio occultation. And the main point, so this is basically showing a number of traces where we can collect radio occultation profiles very near the satellite, because that's what you're most interested in. I don't have much time to discuss what radio occultation is about, but it more or less allows you to scan the electron content along the ionosphere through the rays up to the GNSS. But if you have nice configuration, you basically do this close to the satellite as you go down in terms of altitude. And the configuration is very nice because the GNSS satellites, they basically are 55 degrees, 56 degrees in terms of inclination. And it's nice to have a similar inclination in this respect. So we've witnessed this. It really is a nice configuration for this as well. I mentioned high frequency signals, and here I'd like to, oh, by the way, one thing I should mention, Dania said that has been a recent release of an update, a new version of all the data. We've just released the burst data from Swarm in the latest version as well, consistent with the update that has been made. And the reason I'm mentioning this is that these burst data that allow us to detect signals that we call whistlers. They're produced by lightning. And the point is that when you get those lightning, they produce a kind of a peak that propagates in the ionosphere, and then they get dispersed, and you get this characteristic signal of a dispersion. And this provides some information about the electron content along the path. The interesting thing about this is that it allows to have some information below the satellites. GNSS always provide you with information above, or possibly scanning using radio occultation, but you rarely get information from below because you're not looking downwards. So this is an opportunity to also get some information about the ionosphere below the satellites. Okay. In the case of NanoMagSat, the point is that we want to capitalize on what we've seen with Swarm, but now that's why we have 2 kilohertz signals rather than 250 hertz on Swarm. So that allows to see a lot more. And the whistlers, by the way, are not only the only signals at these frequencies. So there's a whole area of interest for waves propagating in the ionosphere with NanoMagSat as well. I mentioned the fact that we would have the Langmuir probe working at high frequency, 2 kilohertz. So if we have the combination of the vector field, and so that allows us to scan field-aligned currents, for instance, at a very fine scale, plus the electron density as well, so that the idea is to access scales that we currently do not access. They've been accessed through Langmuir probes on a number of satellites, sounding rockets, etc. But this was never done with a magnetometer working simultaneously. So there's an interesting opportunity here as well. So I'll try to finish. I don't know how long I've been, but with the magnetometry payload. So coming back to the status of the mission right now. So we're in phase B, and the hardware is always very advanced. So the instruments do exist in various versions, like engineering units and stuff like that. So here, just this is showing the so NanoMagSat deployed. And the picture you see is describing the boom that is folded with the optical bench, and you get the star trackers and the MAM, which is the absolute magnetometer, providing also the vector field at 1 hertz. And everything is compact because it's 16 new satellites, so it's quite small. It's roughly 20 by 20 by 40, a little more centimeters. And it's roughly 30 kilogram, 35 kilogram. And there has been a lot of developments specific for NanoMagSat, starting with the boom, but also for the star trackers. There are deployable baffles that have been designed by DTU, and of course some progress in miniaturization for the various instruments. On the multi-needle Langmuir probe, so this one has been run on various missions in the past, but the characteristics here is that we want to run it in a okay, I don't know how familiar you are with the Langmuir probe, but the idea is that you have probes, you have voltage between, you impose the voltage, and then you capture some currents. And there are the various ways. Either you have a single needle and then you sweep the voltage and you see how the current is responding, but that takes time, which is why standard Langmuir probes usually are at 1 hertz or a few hertz. But here the idea is that if you have several Langmuir probes acquiring simultaneously at fixed voltage, then you can reconstruct at higher frequency. But the idea is we want to run 3 of them in this way and 1 the standard way, so we can also access electron temperature. So that's a new way of doing things. And here you can also see the GNSS antenna. There are 2 of them at the front and RAM and aft, and for the radio occultation, and there's 1 on top for tech and precise orbit determination as well. That's the boom again, because this was, so it's a 3-meter boom, compact into 20 centimeters when it's folded, so you can see it partly deployed with the optical bench. And on that picture, you don't see the instruments, it's just the boom itself. And of course, you'll have to deal with all the harness and stuff like that. So it's quite a challenge, but it works, at least on the ground for the time being. And this is the overall mission architecture, the way we will operate the mission. So the idea is that they will be launched, and that's Open Cosmos, the company we're working with, building the satellites and operating the launch. I mean, managing the launch, then operating the space segment and the ground segment. They basically have the connections with the communication with the satellites. They collect the data, then it is sent to us within IPGP, where we'll be process it into the standard level. Well, in the ESA language, normal language, it's called level 1 and level 2, where we now have level 1A, level 1B for Swarm, etc. But that's the whole idea. And there's the role also of the science advisory group. And then the idea is also to capitalize on the science community to actually get higher level products, including the disk. That's the status. That's where we are. So the idea is that we will launch in 2027. Right now, we're working on having the launches secured, etc. But the target is to launch actually possibly mid-2027 for the first satellite, because that would be the polar satellite. And Anya mentioned that we will have a workshop in Potsdam, so that's correct. It's Potsdam, by the way, not Postdam. And I guess this is. I just want to mention. So that's NanoMagSat. Niels mentioned what would go beyond, but one thing we're working on with Open Cosmos and a number of things is that we want also to work on the possibilities for collecting efforts from other countries who right now have not necessarily developed space missions, to contribute to these type of nanosatellite, which are much cheaper, because an individual satellite now the cost is roughly 5 million euro. So we're trying to figure out how we could possibly expand the constellation in a collaborative way, a little bit like we run the intermagnet observatories. And that's it, I think. Thank you.